The following is a demonstration of Newton's three laws of motion by Jerry Watkins for Physics 101 at Klamath Community College. Newton's first law of motion states that an object in motion will remain in motion and an object at rest will remain at rest unless acted on by an unbalanced force. In other words, an object will not change its motion unless a force acts upon it. An object that is at rest will remain so until something pushes or pulls it. An object that is in motion remains in motion until something pushes or pulls it. All objects resist having their motion changed. This tendency to resist a change in motion is called inertia. The more mass an object has, the greater its inertia. For my first demonstration, I will be placing a nickel on top of a piece of paper over a glass. I will then pull the paper quickly away from the glass. The nickel will remain in place and fall into the glass. An object at rest will remain at rest, so when I pull the paper out, the nickel will remain at rest. Its inertia will keep it from moving with the paper. The paper moving underneath the nickel will introduce a very small amount of frictional force, but not enough to significantly move the nickel. Once the paper is out from underneath the nickel, a force will be applied to it in the form of gravity, and it will fall into the glass. For my second demonstration of Newton's first law of motion, I will take a stack of nickels and place them on the table. I will then take another nickel and I will flick it towards the pile. When the nickel I flick towards the pile strikes the nickel on the bottom of the pile, it will introduce a force to that nickel which will cause it to move. However, the inertia of the nickels stacked on top of that nickel will keep them from moving with the bottom nickel. The bottom nickel will move off from the force applied from the flicked nickel, and the flicked nickel will change trajectory basically in this demonstration and move off in another direction. But the remaining nickels will fall straight down to the table under the force of gravity due to their inertia. Newton's second law of motion states that the force of an object is equal to its mass times its acceleration. A change in motion occurs only if a net force is exerted on an object. A net force changes the velocity of the object and causes it to accelerate. If an object is acted upon by a net force, the change in velocity will be in the direction of the net force. The acceleration of an object depends on its mass. The more mass an object has, or the more inertia it has, the harder it is to accelerate. More mass means less acceleration if the force acting on the object is the same. For my first demonstration of Newton's second law, I rolled an object with a mass of 0.42 kilograms down an inclined plane where it crashed into an object with a mass of 0.25 kilograms. The object at the bottom of the incline moved 17 centimeters. I then rolled the same object down the same inclined plane, and it crashed into an object with a mass of 0.37 kilograms. This object only moved 11 centimeters. Newton's second law states that the force exerted on an object is equal to its mass times its acceleration. The force exerted on both objects was the same. The object with lower mass accelerated more and therefore moved a further distance than the object with a higher mass. This illustrates that for the same applied force, the acceleration, and thus the distance moved, of an object is inversely proportional to its mass. The object with less mass accelerates more and moves a greater distance compared to the object with a higher mass, which is in line with Newton's second law. For my second demonstration of Newton's second law, I will roll two objects down an inclined plane simultaneously. One of the objects, a cork from a wine bottle, has a mass of 0.006 kilograms. The other object, an impact socket, has a mass of 0.42 kilograms. According to Newton's second law of motion, the more mass an object has, or the more inertia it has, the harder it is to accelerate. More mass means less acceleration if the force acting on the objects is the same. In this case, the force acting on the objects is gravity, and therefore will be the same. So in this demonstration, we should expect the object with less mass to accelerate at a faster rate than the object with a higher mass. I'll slow this down so we can see better. And so clearly this demonstration bears out Newton's second law. Newton's third law of motion states that for every action there is an equal and opposite reaction. When one object exerts a force on a second object, the second object exerts an equal force in the opposite direction on the first object. The force exerted by the first object is the action force, and the force exerted by the second object is the reaction force. For my first demonstration of Newton's third law of motion, I have two cylindrical objects. I will roll one of the cylindrical objects so that it crashes into the second one. The first object will impart an action force on the second cylinder. The second cylinder will impart a reaction force in the opposite direction on the first cylinder. This results in the second cylinder being put into motion, moving away from the first cylinder. The reaction force causes the first cylinder to slow and stop. This demonstrates the action and reaction forces described by Newton's third law of motion. For my second demonstration of Newton's third law of motion, I'm going to make a cannon out of a water bottle and a wine cork. Fuel for the cannon will be effervescent tablets, aka Alka-Seltzer, and water. I'll fill the water bottle about 2/3 full with water, and then I will break up the effervescent tablets and drop them into the water bottle. Then I'll cork the bottle and set it on the ground on my line that I previously marked with tape. The pressure is going to build inside the bottle as the effervescent tablets dissolve, creating a gas. As the pressure builds, the gas will exert an action force on the cork, and the cork will exert a reaction force in the opposite direction on the gas. When the force builds to a high enough level, the action force will cause the cork to fly from the bottle. The reaction force from the cork will force the gas in the opposite direction back into the bottle. This will cause the bottle to move in the opposite direction, since the gas will exert an action force on the bottle. At the same time, the bottle will exert a reaction force in the opposite direction on the gas, forcing the gas from the bottle as the bottle travels backward from the action. The cork shot out so fast you can't even see it. But the water bottle moved about 3 inches, 4 inches maybe. The differences in mass result in the cork accelerating faster and thus traveling much further than the water bottle. The cork traveled about 12 feet versus the 3 or 4 inches that the water bottle traveled. That's it. Thanks for watching.